Welcome to this video. Here we are going to discuss about demand paging. Demand paging is a memory management scheme used in operating system to improve memory usage and system performance. Demand paging works similarly like instead of loading the whole program into memory at once, the operating system loads only the necessary parts of the program. Only it is needed. So instead of loading entire program into memory, only the required portion will be loaded into that memory for execution. So demand paging is a technique used in virtual memory system where pages enter main memory only when requested or needed by the CPU. If it is not required, then it's let it be in that disk till it has been required by the CPU. Demand paging, the operating system loads only the necessary pages into the uh, memory at runtime instead of loading the entire program into memory at the start. So here page fault occurs when the program needed to access page that is not currently in memory. If CV needs one part of the program, it's not available in the memory is called page fault. Then operating system loads the required page from disk into memory and update the page table accordingly. The process is transferred to the running program and it continues to run the if the page had always been in memory. So demand paging with swapping, pager guesses which page will be used before swapping out again. Instead, pager bring in only those pages into memory. Here we need memory management unit functionality to implement demand paging. If pages needed are already memory resident, here no difference from non-demand paging. If pages needed and not in the memory, they need to detect that load and the page into the memory for execution from storage without changing the program behavior. The demand paging, here it could bring entire, okay, instead of bringing entire process into memory, only the required will be loaded into memory. The advantages, less IO needed, less memory needed, faster response and more users can use. It's for multi-programming, it will be useful. Similar to paging system with swapping. Here the program A and program B in the memory. Okay, here what happens? These things are available in that secondary disk. It's a storage secondary disk. Only the required portion of this program A will be available. Then you want to load program B. Then this remove that program A and store it in the disk and load the program B into that main memory. So here we have a concept called valid or invalid bit. With each page table entry, a valid or invalid bit is associated. V is something but valid bit. This is available in the memory. The particular page is not in that memory. It's called invalid. See, this see some pages are available in the memory. Then that will be a valid bit. Okay, here the remaining will be invalid. That means it's not having information about the pages available in the memory. So during MME address translation, if valid or invalid in page table entry is I. So page table, here it's a logical memory. Assume a program with A, B, C, D, E, F, G, H pages. It's a logical memory. Here all these pages are available in the secondary storage. Now the okay, the OS is going to load only the required portion at a time. This A and C and F, only three are required for execution. Only those will be loaded into that memory for execution for better memory utilization. So what happened? The 0 is stored in that fourth frame in main memory. Then here we have this um, this is this second one is C, right? CACF is available. So C is in that sixth one. It is in sixth we have this. Then again F is available in that ninth one. So these three bits are set to valid. The remaining page entries are invalid because there is no page information. Then page fault. The term page miss or page fault refers to situation where a referred page is not found in the main memory. When a program tries to access a page or fixed block of memory that is not currently loaded in the physical memory is called page fault. Okay. Then here before enabling the program to access page that is required, the operating system must bring it into memory from secondary storage in order to handle page fault. So here Operating system looks at another table, decide like invalid reference or just in memory. Find free frame, swap page into frame by a scheduled disk operation, reset table say to indicate page now in memory and set to valid. Restart the instruction that caused the page fault. See what they are discussing is here you want to load M. First you are going to check whether M is available here. It is invalid. That means the M is not available. So give the information to the OS. OS is going to fetch that from secondary disk and load this M into that main memory and update the physical entry with that physical memory entry with that page table. This M is available in particular location, then restart the instruction. So if the required portion is not available when page fault occurs, this will be handled like this by operating system. Then the demand paging aspects are extreme case start process with no pages in the memory. So initially no pages are available, the page fault occurs. Then OS sets instruction pointer to first instruction of process, non-memory resident is page fault. Okay, and every other process pages on first access is called pure demand paging. It's also based on that locality of reference. Then performance of demand paging. Okay, the stages in demand paging are investigate, trap the operating system, save user register and process state, determine the interrupt was a page fault, check that page reference was legal and determine the location of the page on the disk. Then we have to raise the issues to read from disk and to a free frame. Wait queue for this device until read request is serviced. Wait for the device, seek and or not latency time. Begin the transfer of the page to a free frame. Then next step, while waiting, allocate CPU to some other user. Receive an interrupt from the disk IO system when IO completed and save the registers and process state for the other user. Determine the interrupt was from the disk, correct the page table and other tables to show page in is now in memory. Wait for the CPU to be allocated to this process again. Restore the user, registers, process state, a new page table and then resume the interrupted instruction. Then there are three major activities: service the interrupt, read the page, restart the process. Then here for example memory access time is 200 nanoseconds, the average page fault service time is 8. Then the expected access time EAT is equal to 1 minus page fault into 200 plus page fault into 8 milliseconds. In this case average of 8.2 time the page fault service time is there. Then demand paging optimization. Here swap space IO faster than file system IO even if on the same device. So swap allocated to large chunks, less management needed than file system. So it copies entire process image to swap space at process load time, then page in and out of swap space. So demand paging in program binary on disk, but it discard rather than paging out when the freeing frames. Copy and write allows both parent and child process can share the same program in memory. It allows more efficient process creation as only modified pages are copied. For example, here process 1 and process 2 both are sharing this ABC. Before this, if page C is modified, then we have to have the copy of this page C. This is created after modifying this. So what happens if there is no free frame? We have to go for the replacement policy. Here the replacement finds some page in memory but not really in use. Paged out. So we can go for different policies. First in, first out, LRU, we'll discuss. So prevent over allocation of memory by modifying page fault service routine to include page replacement. The modified bit or dirty bit is used to reduce overhead of page transfers. The page replacement completes separation between logical memory and physical memory. Here, need for page replacement. Here we have this 3, 4, 5 are available in page table. It's for user 2. Here what happens, this page 0 here, this B and M. Okay, this M and B Both are available in the second disk. The only things like 0, the page 0, this one is 0, we have this, it is in 3. So go to 3 and check yes, H is loaded. Then 1, load M is not there before loading it. It's in that secondary disk. Then 2, J, go to that 5, it's there. Like that we have for user 2. So here if this MS or B is not available, then you have to find the free frame and replace that. So basic page replacement policies: find the location of the desired page or the disk, then free frame. If there is a frame, use it, otherwise replace that. Select one frame, it's called victim frame, and just make it as a dirty bit or invalid, and just replace that bit with new one. So bring the desired page into that new frame, update the page and frame tables. Continue this process by restarting the instructions. So here page replacement, here first step is find the victim. Okay, find the victim where you want to place, then change this value into invalid and swap desired location from memory disk into that victim page and make this as a valid bit. So frame allocation algorithm determines how many frames to give each axis, which frames to replace. Okay, the page replacement algorithm, it wants lowest page fault rate on both first and z-axis. Then evaluate algorithm by running it on particular string of memory, the references and computing the number of page faults. Then the string is just a page numbers, not full addresses. Repeated access to the same page does not cause a page fault. Results depend on the number of frames. For example, consider reference string, it's a page number. Here, this is if page fault occurs when number of page frames increases, it reduced. First term, first out. First in, first out. See the reference string. Here we have only 3 frames. Then 7 is placed here. Page fault occurs. 0 is not here. Loaded. Page fault occurs. 1 is loaded. Now we have no free space. Then where will we load the 2? Which one comes first? That is going to be replaced. Now the 2 will be loaded in that. Again the page fault occurs. Now 0 is available here. So it is page hit. Then 3, which come first? Then 0, we are going to replace this 3. Then 0, so keep on moving like this. There are around 15 page faults. So here there may be chance of this Bernoulli's anomaly. It's a phenomenon in operating system where increasing the number of frames in memory leads to an increase of number of page faults for certain page replacement algorithms. Normally, the more page frames are available, the operating system have more flexibility to keep the necessary page in memory, which should reduce the number of page fault. Then optimal algorithm. Optimal algorithm, the page will not be used for longest period of time. Replace it. Okay, here 7 will be loaded here, the 0 will be loaded here, the page fault occurs, 1 is already loaded. Now 2, where will we load, which is not used for longer period of time, 7, 0, 1. So replace 7. Again 0 is hit occurs, no page fault. 3, which is not used for longest period of time, 1. Replace it. Then again 0 is there, hit occurs. Then 4, which is not used for longest period of time, then replace. So keep on moving like this. This is about optimal algorithm, the least recently used algorithm. Okay, it's for past knowledge rather than future. Okay, which is not used for long, which is not used recently. That is going to be replaced. Replace page that has not been used in most amount of time. So here load 7, page fault occurs, 0 loaded, 1 loaded, then 2 values, 7 is not used for longest period of time compared to 0 and 1, loaded 0, it's there, so hit occurs. Then 3, again 0 is recently used, among this 0, 3, the 2 is not used for longest period of time, so it's moving. So there are 12 page fault occurs. Then LRU. Okay, counter implementation. Every page entry has a counter. Every time page is referred through this entry. Okay, copy to the clock to the another. So you can go for either stack or counter implementation. The LRU and opt or cases stack algorithm, you don't have Beldis. Here the stack, here we have the reference string, stack before and after the stack. Okay, it's going to have the stack, the top is having it, which is not used for longer period of time. Then LRU approximation algorithm, we have this reference bit and a second chance algorithm. The reference bit, each page associate a bit initially 0. In pages referred to a bit set to 1. Replace any with reference bit is equal to 0. Or second chance algorithm, use the clock. The page to be replaced, it has reference bit is equal to 0, replace it 1 in a, then set reference bit is equal to 0, leave page in memory. Replace next page subject to the same rules. So this is the second chance page replacement algorithm. Then enhanced second chance algorithm. Improve this algorithm by using reference bit and modify it. Take ordered pair of 0, 0, 0, 1, 1, 0, 1, 1. 0, 0 neither recently used, not modified. Then not recently used but modified. This is for recently used, this is for modified. This is recently used but not modified. Both recently used and modified. Then counting algorithms, we can go for LFU and MFU algorithms. Page buffering algorithm, keep a pool of free frames. Always possibly keep it modified pages. Possibly keep free frame contents intact and not with that. So applications of page replacement. All of these algorithms have OS guessing about future page access. Some applications have better knowledge, that is databases. Memory intensive applications can cause double buffering. The OS keeps copy of page in memory and as IO buffer. Then applications keep page in memory for its own work. So operating system can give direct access to the disk getting out of the way of the applications. Example raw disk mode. Then bypassing, buffering and locking, etc. So this demand paging is mostly used for using virtual concept, which is for loading that desired pages into memory for execution. Thank you.